All right, guys, before we get into this here, a couple of reminders, okay, that your Unit 3 exam that we're reviewing for today is on Tuesday, okay, and I also put up on the board when your Unit 4 exam will be, because that unit's really short, and well, we're almost done. So June the 12th is going to be the day of that one, okay. We are going to be kind of rushed in the last units, okay. No way around it. We spent some extra time on graphing we probably didn't have, but it was worth it. But it is going to make the last unit have to be kind of condensed. Okay, so you will have a unit exam for that one on Thursday, June the 12th. Okay. Also a reminder that the final deadline for any overdue assignments will be June 13th at 12:20. Okay, make sure you have any assignments you want in for grading in by that time. And of course, you have to have all of your assignments in to write the mock or be eligible to write the mock. Okay, so first thing we went over in this unit were the types and forms of energy. Okay, so that was like chemical energy, kinetic energy, nuclear energy, mechanical energy, okay, those kind of things. They're going to be multiple choice, maybe numerical response kind of questions. Be able to identify what kind of energy is being talked about in an example. Okay, so if I told you, that there was, like yesterday, there was a whole bunch of wind. Okay, what kind of energy would that be? Well, it would be, if your options were kinetic, potential, chemical, and nuclear, I would probably say kinetic would be your best bet on that one. Okay, so that kind of thing would be probably the type of thing you'd be asked. Okay, so make sure you go over the types and forms of energy. Just know them well enough to be able to identify one from a given situation. Okay, you need to know the three types of systems: open, closed, and isolated. Again, that's going to be multiple choice, numerical response, just recognize and recall kind of stuff. Okay, remember, an open system exchanges matter and energy with its surroundings. A closed system exchanges only energy, and an isolated system exchanges neither. Then we talked about thermodynamics and heat pumps. Okay, so heat engines, heat pumps. Remember, you need to know the first law of thermodynamics. Energy can't be created, it can't be destroyed. Okay. Second law of thermodynamics, energy flows from high to low, hot to cold. Okay. Probably some application stuff, but that is again also mostly going to be multiple choice, numerical response kind of stuff. Okay. All right, for the heat engines and heat pumps, those revolved around the second law of thermodynamics. A heat engine uses the second law. Okay, so like a jet engine was a heat engine. There's the area where the fuel is burned. Everything wants to go from hot to cold, and that would produce a thrust that propels the plane forward. Whereas something like Coolio over there, okay, like the air conditioner, that's a heat pump. It's using energy to pump heat into the hotter area. That's against the second law of thermodynamics. We can break the law of thermodynamics, the second law, but we have to put energy in to do it. We can force the heat to go the other way, but it's like pumping water uphill. All right, everybody with me there? All right, so know those, be able to recognize those, okay? Perpetual motion machines, okay, we talked about how the laws of thermodynamics say that you can't have one of those, okay? It wouldn't be able to do any useful work, right? And it would have to be a completely isolated system because energy always flows away from a high energy object or system. Okay, then we talked about scalars and vectors. Okay, let's leave your phone. Okay, so scalars and vectors, okay, that's the V equals D over T stuff. Okay, make sure you know which things are scalar. That would be distance, speed, time, energy. Okay, and know which things are vector. Velocity, displacement, acceleration, force. Okay, all of those things. Not so much because I'll have like a multiple choice question, which of the following are vector quantities. I'm more than likely not going to do that. But here's where that becomes important. What if I give you an acceleration problem where I give you the acceleration, okay, I give you the initial velocity and the time, and I ask you to calculate the final velocity. And you write 3 meters per second. Are you getting that right? Because you didn't put what on it? You didn't put a vector on it, right? It might be up or down or left or right, okay, or something like that. So if a question is asking you solve for this, one of the things you've got to be able to do is go, is that a vector quantity or a scalar quantity? Because you solve for them differently. Okay. All right, so scalar and vector quantities, okay, that was mostly v equals d over t. Okay, so here are our scalar quantities: speed, distance, time, energy, okay, velocity, displacement, acceleration, and force. And it was also in this topic, like we said, where we went over v equals d over t. Now remember, there are 2 different forms of v equals d over t. Okay, there's v equals d over t, that is speed is distance divided by time, and there's this one. Velocity is displacement divided by time, which can also be written like this: final position minus initial position divided by time. Okay, one is vector, the other is scalar. The place you'll most likely use those 2 formulas is on graphing questions. Okay, I'm not going to have a 4-mark problem involving manipulating v equals d over t. Okay, we're past that. But it could be part of, here's a position versus time graph. Okay, what's the average velocity between 10 and 20 seconds or something like that? Then you would have to use this. Everybody with me there? All right, then the thing we probably spent the most time on in this whole unit, graphing. Okay, so on your exam, there are a number of graphing questions. There are some in the multiple choice. There are some in the numerical response, okay, and written response. I'm not going to ask you to do anything on this exam that we haven't done several times in class. So expect that you're going to get one graph that's linear. That means you'll use y equals mx plus b, and I'll give you that equation. It'll say on there y equals 3.52 plus or times x plus 10.5 or whatever. I'll give you the equation for the line if it's a linear graph. If I give you the equation for the line, should you use it? Yeah, don't try and do something else. Okay, if you're given a linear graph and you're given the equation for that graph, don't try and freelance it. Okay, I'm giving you the equation for a reason. I expect you to use it. Okay. And you'll get an irregular graph. Okay, I mean, you're going to get for sure one of each that involve doing calculations, okay, in the numerical / written. Okay, so you'll have to do some calculations. You'll have to do that stuff. You'll also get some graphs in the multiple choice. Those won't involve calculating. They'll involve interpreting. Okay, so I show you a graph and I ask, what's going on in this graph? A, object's not moving. B, object is accelerating. C, object traveling at a constant velocity backwards. D, at constant velocity forwards. Okay, you'll have to be able to interpret the graph and decide what's going on. Okay, that kind of thing would be a multiple choice question. Okay, so if I give you y equals negative 2.5x plus 38, what's that graph going to look like? Right? Stella drew it in the air there, and she was totally right. Like that. Okay, that has a negative slope, right? There's a negative sign in front of the slope. Okay, that means that it's going down, okay, at 2.5 whatever, okay, every time interval. So the slope would be negative 2.5, okay, and my y-intercept would be way up here at positive 38. Okay, now if I gave you a graph like that, maybe I would ask, let's say it's a position versus time graph. So this would be meters, this would be seconds. If I asked you to calculate where the object would be after 30 seconds, are you solving for y or x? Where the object will be after 30 seconds, y. Where is position? Yes? I gave you 30 seconds. Seconds is on the x-axis. I gave you x. I asked you to calculate y. Right? If I asked you how long would it take to go 100 meters, that would be solving for x, because then you're solving for time. Okay? So being able to use y equals mx plus b, definitely something I'm testing on your unit exam. Okay, so we could also get an irregular graph. Maybe something like that. Right? Let's say that this is a velocity versus time graph. Okay. What if I asked you to calculate the acceleration between 10 and 15 seconds? Okay, would you be able to do that? Provided I actually had numbers on here, yes. Okay, you would use that formula. Okay, because you could read those things right off the graph, right? What's on a velocity time graph? Velocity and time. I could plug numbers into that formula from that graph. What if I asked you to calculate the displacement between 0 and 10 seconds? Then what would you do? Draw the shapes. Okay, you got to use average velocity times time, right? For this first little bit here, that object is traveling at a constant velocity, so I can just go average velocity times time. That's base times height. All right, then I would have this little triangle here, I'd have this big long rectangle and that triangle there. Okay, I'd calculate all those areas. That's average velocity times time, add them all together, and I've got my displacement during that time. I will definitely ask you to do that. All right, and then expect an acceleration problem, okay, in the written part, and you have to know what acceleration is for the multiple choice. I'm going to ask you questions about the nature of acceleration in the multiple choice and ask you to do calculations and problem solving in the numerical and written response parts. Okay, so be able to use that formula, manipulate, and solve for any part of it. Okay, then we went to work energy theorem, okay, which is actually quite a bit more recent. Okay, work energy theorem says that work is a change in mechanical energy. Okay, for us in Science 10, that'll be either kinetic or potential. Okay, you guys were getting pretty good at this, so I'm not too worried about it for you. All right, remember that this can expand out. This, force times distance, would be our final energy, be it kinetic or potential, okay, minus our initial energy. All right, and then at that point, you plug in and you start manipulating and solving. Okay, it's just algebra. Should you understand the work energy theorem well enough to answer a multiple choice question about it? Okay, multiple choice question is not going to involve any calculating. It's going to involve, can you understand when work is being done versus when it's a conservation of energy situation? Okay, so if work is being done, the energy is being changed. Look for any context that in a common sense fashion would seem like you're changing the energy. You're pushing a rock up a hill. okay? You're lifting, something up. You're pushing something and making it go faster. All of those are things that involve doing work. Okay, all right, so be sure to be able to identify when a work energy theorem, or when work is being done. Okay, that would be the big thing. Okay, and then we got conservation of mechanical energy. Okay, that's what we were working on the last 2 days. Right, in that situation, no work is being done. The initial and final energies are equal. So that would be like a roller coaster or a sled going down a hill or something along those lines where there's no other forces. And the object is just doing what it would naturally do. Okay, and then the one thing we haven't gone over yet, because we're going to go over it on Monday, is efficiency. Right. Now, I'm just going to introduce efficiency to you here, so you have, probably something you've heard of before. Okay. Efficiency is basically the percentage of the energy you put into something that actually ends up doing what you want it to do. Okay, so for example, if I go and put gas in the tank of my car, okay, I might put into there 50,000 joules worth of chemical energy. But in driving my car around, my car only does 20,000 joules worth of useful work. Okay, what happened to the other 30,000 joules? Well, it didn't do useful work, okay, which makes my car not very efficient. Okay, so efficiency is just a percentage. Okay, so if I put in 50,000 joules of energy into my car, but it only did 20,000 joules worth of useful work, my car is running at 40% efficiency, which for a car is amazing, actually. Most cars run around 20. Okay, hybrid cars maybe a little better. I'll show you how that works on Monday. Okay, but efficiency is obviously something that's important. We want to be able to use as much of the energy we put into something to do what we want. We don't want to waste it. Okay, wasted energy is just stuff that didn't do anything good. Okay, it turns out as heat, sound. Okay, stuff that's not doing what you want. All right. Let's talk about the layout of your test here. All right, so you will have 20 multiple choice questions. And 6 numerical response questions. And 5 written. Okay, there are 29 marks in the written. Okay. The formulas I did put on the front page of the exam. Okay, so you will not be allowed to have your formula sheet for the test, because I don't know how many notes to self or different variations of each formula you have written on your periodic table. Okay, so the formulas are on the front page of the test. Those are the ones that you can have. Right? Incidentally, on the final exam, you will also get a fresh periodic table. You are not bringing yours to the final. Okay? All right. Questions from you guys? Anything you want me to go over in more detail? Some other questions you'd like me to go over? I am going to put a review package on Google Classroom today, so you can have a look at it over the weekend. No. No. I mean, no Jewel. He's important. Yeah, but no, I'm not worried about whether you know like Orsted or Faraday or those guys. Like, don't remember putting it. Let me just double check. I don't remember putting any names on here. Zero names. Okay, other questions? Names, there are no names. I'm not gonna ask you, what did Orsted do?
Oh, okay.
Incidentally, he was the one with the current carrying wire who showed that a current makes a magnetic field and it moves the compass. But you don't necessarily have to know that. What else? Okay. I will throw the review package up here then. You guys can have a look at that. So I will put this on Google Classroom so you can have a look at it over the weekend here. I wouldn't worry about question number 3 because that's names. Yeah, I recently changed the exam to not include names, so you won't have to worry about CVEC, Volta, or Orsted. Okay. CVEC made the thermocouple, Volta did the first battery, and Orsted did that magnetic field thing. But you don't have to worry about that. Okay. There's just some stuff in there to help you kind of go through your notes and write down important concepts, you know, like the 3 types of systems and things like that. Okay, and then there are some problem-solving problems there. These are old exam questions. Okay, the answers are there in bold, so you can check and see if you've done them right when you're working on them. Okay, so like I say, some of every kind. There's some graphing stuff in there as well. Okay, for you to even try as some practice there as well. Okay, and all the answers are in there. So I will post that on Google Classroom. Okay, but for right now, I would say start at like question number 5.
Can you make it a little bit bigger?
Better?
That's
Okay. Now, just so you know, guys, this is the only review material you're getting. There's no practice test. I'm kind of weaning you off of those. Okay, you had those for the first 2 units. This is like the practice test. Okay, it has some old exam questions on it. There's no multiple choice, obviously, okay, but you know how I'm going to do those things already.